Hi guys, good morning, good afternoon, and good evening. Welcome to ECE 100 Discussion 2. I hope you're doing well this week. The content is a little bit harder than the first week, but you will all be fine. This discussion will help you master the contents in Chapter 2. After this discussion, you will be able to solve the circuit, which means getting the current, voltages, and power using different techniques. The most basic ones are division, voltage or current division. The more advanced techniques will be node voltage analysis, as well as mesh current analysis. Besides this, you will also be able to do source transformation. And their more complicated name is to get the Thevenin or Norton equivalent circuit. Sorry, there's a typo. Okay, and there is a gentle reminder. If you are still confused with reference polarities, reference direction, and the size of power you calculate, please go ahead to discussion 1 to get a review and then come back to discussion 2, because in discussion 2, I will assume that you already mastered that content. Okay, so let's begin. In the chapter 1, we learned how to compute the equivalent values for a set of resistances. They are in parallel or in series. And the function we get, the equation we get is resistances in series, their equivalent resistance will be their sum, right? And for resistances in parallel, their equivalent resistance will be the second equation. This is what we learned last time. And this will derive the principles of voltage division and current division. For the series circuit, when we times both sides with the variable I, because they share the same current, right? When we times I on both sides, we get the total voltage and the sum of voltage across every resistance element. And to find the voltage across a specific element, let's say across the second resistance, the distribution on it will be this specific R times I, right? So that's how we get the voltage division equation, which is the ratio of the given resistance to the total resistance, which is equivalent resistance of the whole series, is equal to the voltage fraction of the total voltage. That's how we get this equation. We don't need to memorize it. We just need to understand it, then we can use it. And similar things happen for resistances in parallel. But the difference is that the variable they shared is not current, is voltage now. And we know I is equal to V over resistance. And 1 over resistance, 1 over R, is also called conductance, represented by symbol G. So it can also be written as G times V. So pretty similar. The ratio of the given conductance to the total conductance is equal to the current fraction of the total current. And these two equations circled with orange pen are voltage division and current division law. You got it? If you haven't, try to solve the first few questions in the homework too, and you will be comfortable and by getting more familiar with them. Now, let's come to our big parts in this discussion, which is node voltage analysis and mesh current analysis. These two methods are actually two different techniques, utilizing KVL and KCL to solve your circuit. You can choose either of them as long as you're comfortable. And some people will ask, why do we need node voltage analysis and mesh current analysis when we already have voltage or current division? The latter seems more simple, seems simpler, right? So why do we need that? And I'll say, your thinking is right. Voltage and current division, they are much more intuitive and convenient to use. But sometimes they cannot solve a more complicated circuit, so they will be not applicable in some cases. When they are not applicable, we need some new techniques, more powerful techniques to help us solve the circuits. And that is where we need these two powerful tools. You will agree with me when you see this circuit. First, let's try to solve it by using only voltage or current division. In that way, we need to find which resistances are in series or in parallel. So can you find any resistances in parallel? The answer is no. And can you find resistances in series? The answer is no either. So now we have to ask for help. Let's go to node voltage first. There is something I want to remind you. The first thing is that any node can be a reference node. But usually we just set one end of a voltage source to be the reference node. For example, in this figure, we set the negative end of voltage source to be the reference node. We can call it node 0 for convenience. We choose this node instead of other nodes because this will help simplify our problems. Let's first give names to other nodes as well, so we can communicate more efficiently. See, given the negative end of the voltage source as a reference node, we can immediately get V1 at node 1, right? So V1 is equals to Vs. So we don't need to write the KCL equation at node 1 now, because we already know V1. The second thing is that you guys may be confused that we used to say that a voltage has its positive and negative polarities, but why we have the voltage at one node instead of two nodes across two nodes, right? So the fact is that the reference node acts as the negative reference polarities for all the voltages. So the node voltage V1 is actually the voltage between node 1 and node 0. The node voltage V2 is actually the voltage between node 2 and node 0, which means across R4 here. And similar to V3. And when we try to compute I3 at node 2, some people will ask, why do we subtract V3 from V2 instead of the opposite? This is because following the KVL in the loop containing 0, 2, and 3, we'll find out V2 is equal to this, right? That's how we get the expression for I3 here. Before you get familiar with all the reference stuff, I recommend you to literally draw the reference polarities of the voltage as well as the reference direction of the current you want to compute. And once you get familiar with that, you can skip this step. After all these reminders and clarifications, let's get ready to seriously solve it. At node 1, we can directly get V1 equals to Vs, so no need to write down the KCL equation here. And at node 2, let's redraw node 2 to get a better understanding. Let's assume the reference directions are all going out of node 2, and the sum of them should be equal to 0. And the current going out of 2 towards right is I3 here, and the current going down across the R4, let's call it I4 here, and the current going through the resistant 2, let's call it I2 here. So we know that I2 plus I3 plus I4 equals to 0. And let's break it down one by one. How to compute I2? Something between 0 and 2, and something between 0 and 1. We don't care what they are because we already represent the voltage at node 2 as V2 and voltage at V1 as V1, at node 1, sorry. Let's assume R2 is following the passive configuration, which means the currents flow from the positive end to the negative end. In this way, V of R2 divided by R2 will equals to I2. And V of R2 is the positive polarity voltage minus the negative polarity voltage, which is V2 minus V1. And their subtraction over R2 will get us I2. So under passive configuration, the Ohm laws should be V equals to IR. And let's see what difference we have if it is not following the passive configuration. We still discuss the R2 resistance to remain consistent. This is R2, something here, something here. We don't care. See, this time, let's assign the positive polarity on the left end and the negative polarity on the right end. Right? You can see that the reference polarity is different this time, so it is not passive configuration. In this way, we should write Ohm laws as minus IR, V equals to minus IR, because it is not following the passive configuration. And in this way, what do we get? We get that minus V of R2 over R2 equals to I2. Please observe the differences between the two cases. And in this case, the polarities of VR2 is different, but the result is still the voltage at higher end subtract the voltage at lower end. And in this case, it should be V1 minus V2. Resistance is not changed, so let's just write it down. And most exciting part is almost there. Because we have a negative sign in the equation, we need to simplify the result. And what you get is completely the same as the other configuration, right? So the lesson we learn here is that the reference polarity does not affect your result. But this one is more convenient, and I recommend you guys to choose the passive configuration to make your life easier. Okay, we spent some time on I2, so I will skip for the detailed procedure for I3 and I4. I3 let's write the polarities here, is equals to the voltage at higher end minus voltage at lower end divided by R3, sorry. And I4 here is basically V2 over R4, right? And remember, this values always correspond to the reference direction of current you choose. In this way, we will get the KCL equation in terms of node voltage. This is how Professor Farid derived. To complete the problem, let's solve for node 3. Now you can see the current direction here is opposite to I3. So its value will become minus I3 now. Following KCL, we can get I1 plus I5 plus minus I3 equals to 0, right? You can also make your life easier by leaving the I3 as original. The equation is still right. And I1 equals to the voltage at higher end minus voltage at lower end divided by R1. I5 is basically V3 over R5. And minus I3 is basically V3 minus V2 over R3. And then we can get the equation, which is just substituting. Right? Now we have 3 equations with 3 unknowns. We will be able to solve them uniquely. And after we get the values of V1, V2, and V3, we will be able to calculate all the rest elements, like the current, the power, cross elements, etc. But a new problem comes out. What if we have more than or equals to 2 voltage elements in the circuit? How can we choose a reference node? And also, I don't have idea about the resistance or currents flowing through that voltage source. Well, that's a great question. That's why we need to introduce a concept called supernode. So supernode basically means that you draw an enclosed circle to contain the voltage source. Something like this. And you say that the whole thing is a node because it's super big, so it's called a supernode. And then let's track all the current flowing in or out and applying KCL at this supernode. And inside the supernode, we apply KVL like this. So we have the same number of equations as the number of unknown variables so that we can solve it. Is it clear? And some curious students will ask, I still have a question. What if the sources are controlled, like a voltage or current controlled whatever source? Well, my answer is just following all the steps you have learned, doing the same, and add one more equation to describe the relationships between controlled source and the controlling variable. And then you'll be fine. You'll be able to solve it. You'll see the examples in either lectures and Weinan's tutorials. Okay, so we are done about node current analysis. If you still have any questions, please come to my office hour tomorrow. Before we go to mesh current analysis, let me conclude the node voltage analysis with just one sentence. That is to apply KCL at nodes, but represent currents with node voltages variables. And remember the corner cases that involves controlled sources and more than one voltage source. Okay, let's formally start mesh current analysis. One thing to keep in mind is that this kind of analysis approach only applies to planar network. What is a planar network? That means you can find a way to redraw the circuits without having one element crossing over another one. So it means that you can redraw to avoid crossing. If you can, it is a planar network. If you can never find a way to do that, it is not a planar network. Okay? The first reminder is that please know the difference between a branch current and a mesh current. In the figure below, I1, I2, I3 are branch currents. We are familiar with that. But mesh currents are defined by mesh. So the circuit is like a window, and the open areas in between are like panes of glass in the window. And the mesh current is like soaping the panes of glass. Is that vivid? And why we choose mesh currents as the variables rather than branch currents, we are already familiar with that, right? So it must have some advantage. So its advantage is that when you define mesh currents and use them to solve the problem, the process will be easier. We usually don't need to introduce KCL to substitute the unknowns. We only need to solve the mesh currents value. Because mesh currents flows around closed path and they automatically satisfy the KCL. And branch current is equals to the algebraic sum of mesh currents. And for convenience and consistency, we define them clockwise. And let's see, what should be the I3? The I3 is equal to IA minus IB, right? So the steps to solve it: first, draw the mesh currents inside the mesh and make sure they're clockwise. And second, apply KVL in each mesh. And for convenience, we can still using the KVL clockwise. For example, for mesh A, following the clockwise direction, the KVL should be minus VA times IA times R1 plus I3, which is IA minus IB, times R3 equals to 0. And for mesh B, it should be VB minus I3 times R3, and then plus IB times R2 equals to 0, right? Assuming that we already know the values for VA and VB and or resistances, so now we only have two unknown variables. We can solve them by combining the two equations here. And then you will get what you want. And similarly, we wish that our circuit is as simple as this example, but sometimes the case is more complicated. We see that all we encounter here is only voltage source. What if we have a current source? So we have a new problem here. What if current source, right? Because for a current source, the voltage value across it is not defined, it's not determined. In that way, we will introduce one more unknown variables. That is not what we want. So what should we do with it? And my answer to it is, please don't write KVL for loops which have a current source. Use super mesh, or we say a mesh that skips the current source to apply KVL. And for the current source, apply KCL at one of its ends. And sometimes I wish it happened to you is that the current source is not shared by many loops. It is only in one loop. In that way, you will instantly get the values for one mesh current. But usually life is not so easy. In this case, where the current source is shared by two mesh, right? What we can do is use a super mesh that does not include the current source, which is drawn here with an orange rectangular. And please apply KVL to this super mesh. And then apply KCL on the current source, just like we discussed here. So IA plus 2 amps should be equals to IB by applying KCL at this node. And you'll be able to solve it. Oh, I'm so thirsty now. And a new problem, just like we discussed in node voltage analysis, when we find a controlled source, the steps are the same, except you need to add one more equation for the controlling variables and the controlled sources. We are good. Now we come to the 2.6 section of our textbook, which is Thevenin and Norton equivalent circuits. Let's keep it simple. These methods are ways to simplify your circuit. So they are our helpers. Don't be afraid of them. To explain their functions using diagrams is simpler. It's much simpler. So imagine there is a black box consisting of resistances and sources, and maybe it is connected to something else. We don't know what it is. And then we name the two terminals here as A and B. And Thevenin find a way to represent the black box as a voltage source, independent voltage source in series with a equivalent RT. We don't know what is on the right half side, but we just focus on the performance on the left of the terminals A and B. So the new drawing is called Thevenin equivalent circuit. And what Norton did is based on Thevenin's discovery. We find out that it can be also represented using the current source in parallel with a resistance. And the resistance value is still RT, the same as the one in Thevenin equivalent. The N here means Norton, and the T here means Thevenin. And let's give you a brief example about its capability. For example, we have a circuit like this. Just observe it. We cannot solve it by only applying division laws, right? we need to use node voltage or mesh current analysis. And they also have two types of sources. We don't want that. So in this case, we can select this point at terminal A, this point at terminal B. And then we can try to change the left part into a Norton equivalent. They can transform to each other too. So by doing this, an equivalent circuit will look like this. Very good. So now you see that you can combine them and solve the question. Why can they be transformed? Because they claim that as long as you follow their rules to calculate the equivalent voltage, resistance, or current, the equivalent circuit's behavior at the terminals will be exactly the same of the performance of the original circuit. That's why the equivalent circuits work. That's what equivalent circuit means. So let's come to the concrete step of computing the equivalent variables. Here is a black box with resistance and sources. The sources here can be controlled sources, but the controlling variable should also be inside the box. If not, you cannot get the equivalent circuit. Okay? So how do we get a VT? The definition is VT is equals to the open circuit voltage of this box at the terminals, which means that you need to first make it an open circuit at the terminals AB. How to make it? Just assuming that they are connecting to nothing and no currents flow through it, right? This is open circuit. And by assuming that, you calculate the voltage distribution between A and B, and that is a VOC, V open circuit. So we get VT. And the next step is to get ISC, which means short circuit. What is that? That means you need to make it short circuit and compute the ISC flowing through. And after you get this, we compute the R Thevenin by dividing this. And this is a definition. You can Google to see how they derive this. And if there are no dependent sources, which means no controlled sources, you can apply an alternative way to figure out the equivalent resistance. That is to zero or the sources in the box. And for time reason, I will not explain it much in the discussion, but keep in mind, you have that option. For Norton equivalent, the steps are similar. First, make it short circuit. Oh my god, I don't know how to spell it. And find ISC, and then your IN will be equal to ISC. And then make it an open circuit, and the VT is equal to VOC, which is the same as a previous step. And step 3 is to calculate the RT by dividing this over this. Seems pretty similar, right? So their external behaviors are the same. But be careful that same only at terminals, not inside. For example, the currents flowing in RTs in Norton and Thevenin equivalent circuits are not the same. Okay? If you understand this, you're good to go. And one last thing is an extension for that maximum power transfer. In the lecture, we computed the equivalent circuits with a load. And our conclusion is that when RT equals to RL, PL reach is maximized, right? But the thing we need to be careful about is that even it is reaching its highest value, we can see that half of the value is wasted on RT. In reality, we don't use this for big power application, because when the power is when the power is big, big energy. So when the energy is big, you'll find out that 50% of it is wasted on other things instead of load. That is not what we want, right? So, we also need to balance efficiency against this. By making the RL much larger than RT, by voltage division law, we know that VL, the voltage across the load, will also be much larger than RT. And their currents are the same. And in this way, the PL will be much larger than PT. So even if PL is not its maximum, it is much larger than PT, which means that it saves energy. It increases the energy efficiency. So be careful about that when you're designing your own circuits. That is the end of the discussion 2. We have to be careful when we are beginners, right? But on the way getting familiar with all of this, we'll get more and more confident on these problems. Thank you. See you next time. And feel free to ask me questions in the office hour. Goodbye.